Hello viewers, in today's session we are going to discuss an important and very conceptual problem from vectors, and here we are going to see a lot of concepts while solving this problem, right? So let us start and let us first read out this problem in which we are given three vectors, vector A, vector B and vector C, and these three vectors have the magnitudes. The magnitude of vector A is 4, magnitude of vector B is 2, and magnitude of vector C is square root of 2. And we are given this condition, that is the dot product of vector A and vector B is 0, and the dot product of vector A and vector C is also given to be 0. And moreover, we are given that the angle between vector B and vector C is pi by 4, that is 45 degrees. Then we have to show that vector A is equal to plus minus 2 times the cross product or vector product of vectors B and C. And in the second part, we have to show that the scalar triple product of vector A, B and C is equal to plus minus 8. And in the third part, we have to prove that the scalar triple product of these three vectors, that is A plus B, B plus C and C plus A, is equal to plus minus 16. So to solve this problem, we have to make use of different concepts from vectors, right? So now let us start with this condition, that is A dot B is equal to 0 and A dot C is equal to 0. So here the dot product of vector A and vector B is 0, and similarly the dot product of vector A and vector C is equal to 0. Now see, if the dot product of two vectors is equal to 0, then it implies that the two vectors are perpendicular to each other, right? Or the angle between the two vectors is pi by 2. So here a vector A is perpendicular to vector B, because A dot B is equal to 0, and similarly here the vector A is perpendicular to vector C. So we can see that from these two conditions, we can conclude that vector A is perpendicular to B, and also A is perpendicular to vector C, right? So let us geometrically see this situation. So now let us draw the vector B like this, and vector C like this, right? And the angle between the vectors B and vector C is given to be pi by 4. Now vector A is perpendicular to both these vectors, vector B and C. So let us draw the vector A like this. So this is a rough diagram, and here this is 90 degrees, and this angle is also 90 degrees, right? So here A is perpendicular to B and A is also perpendicular to vector C. So now see, a vector B and vector C lie on a plane, right? And on that plane, this vector A is perpendicular. So if vector B and vector C are lying on some plane, then this vector A is perpendicular to that plane, right? So now if we find out the cross product, that is vector product of vector B and vector C, that is if we find the cross product of vector B and vector C, then this vector, that is vector B cross vector C, is also perpendicular to the plane containing vector B and C, right? So it means the vector B cross C is perpendicular to the plane containing vector b and c. Now vector a is perpendicular to the plane containing vector b and vector c. So it implies that vector a must be parallel to the cross product of vector b and vector c. So now we have established that the vector A is perpendicular to the plane containing vector B and vector C, and this vector, that is B cross C, is also perpendicular to the plane containing vector B and vector C. Hence these two vectors, that is vector A and vector B cross C, must be parallel to each other, right? And from vectors we know that if two vectors are parallel to each other, then one vector can be expressed as a scalar multiple of the other vector. So if we have two vectors, say vector p and vector q, and p and vector q are parallel to each other, then vector p can be represented like this, that is vector p is equal to the scalar multiple of the vector q, or we can also write vector q as a scalar multiple of vector p, right? So we'll use this concept over here. So if this is vector p and this is vector q, then this vector a can be written as a scalar multiplication of vector b cross c. So here we write b cross c, where lambda is some scalar and it is some real number. So we have now this vector equation, that is vector A is equal to lambda times the cross product of vector B and vector C. So now taking the magnitude of both sides, we have the magnitude of vector A, and then we have magnitude of lambda B cross C, right? And the magnitude of vector A is 4, and here we can now write mod of, that is magnitude of lambda, and then here we have magnitude of b cross c. So now the magnitude of b cross c is given by a magnitude of b, magnitude of c, and the sign of the angle between vector b and vector c. Let us write it sine theta. So our theta is pi by 4. Now magnitude of vector b is 2, magnitude of vector c is square root of 2, and theta is pi by 4. So here we have sine pi by 4. So this is 2 root 2, and sine pi by 4 is 1 over square root of 2. So root 2 and root 2 get cancelled. So we are left with 2, right? So now we have the absolute value of lambda times 2, right? Now see, we can now write mod of lambda is equal to 4 over 2. Now mod of lambda is equal to 2. So if we solve this equation, we have lambda is equal to plus minus 2, because the absolute value of lambda is equal to 2. So lambda is equal to plus minus 2. So now taking this value of lambda is equal to plus minus 2 over here, we have this equation, that is vector A is equal to plus minus 2, and we have B cross C. So this is our first result which is to be proved. So now to get the second result, what we will do, we'll take the dot product of both sides with vector A, right? So we can now write A dot A, and here we have plus minus 2, and this is B cross C dot vector A. So now A dot A is the square of vector A, and here we have plus minus 2. Now B cross C dot vector A. Now we know that the dot product of two vectors is commutative. So we can now write A dot B cross C. Now from the definition of scalar triple product of three vectors, we know that the notation for A dot B cross C is given by bracket vector A, B and vector C. So this can be replaced by this notation. So we have plus minus 2, we have bracket A, B and C, and here the square of the vector A can now be replaced by the square of the magnitude of vector A, because we know that square of a vector is equal to square of its magnitude, right? And magnitude of vector A is 4, so we have here a 4 square, and here we have plus minus 2 and A, B, C. So 4 square is 16. So here we can now write to bracket A, B and C is equal to 16 over plus minus 2, that is plus minus 8. So the scalar triple product of vector A, B and C is given by plus minus 8. So this is our second result. So now to prove this third result, we are using a direct result from vectors, that is bracket vector A plus B, then we have B plus C, and C plus A is equal to 2 times the scalar triple product of vector A, B and C, right? So here we are using this standard result, and we are not going to prove this result, that is the scalar triple product of vector A plus B, B plus C and C plus A is equal to 2 times the scalar triple product of vector A, B and C. So now the scalar triple product of vector A, B and C, which is proved in the second part, and that is equal to plus minus 8. So we have now the value of the scalar triple product of vector A, B and C as plus minus 8, right? So 2 times 8 is 16, so we have plus minus 16. So this is the required third result.